Okay, in this lesson we're going to talk about the power rule for derivatives. We've already talked a little bit about derivatives, but we haven't spent a whole lot of time on them. So we should know right now that a derivative is going to tell us the slope of the tangent line to a curve. So we spent a lot of time talking about the average rate of change, which was the slope between 2 points. But if we think about the derivative being the slope of the tangent line to a curve, since we're talking about that tangent line, we know that the derivative is going to be the slope of a curve at 1 point. So one way that they can ask about a derivative, instead of an average rate of change, they can ask for an instantaneous rate of change. So, derivative is going to be the instantaneous rate of change. It's the slope of the tangent line to the curve. It's the slope of a curve at 1 point. All of these things are going to be the same exact thing. The power rule for derivatives is going to work on polynomial functions. And I'm going to put a little star by that because there's a couple that of functions that aren't polynomials that we're going to be able to use this on. And we'll say radical functions. And that's pretty much the only exception, because when we think about fractional exponents, that's really just a radical. So what the power rule for derivatives says is that if you have some function f of x that is ax to the b power plus cx to the d power plus ... all the way down to some constant we'll call k, the derivative, which we will call f prime of x, is going to be a times b x to the b minus 1 power plus c times d x to the d minus 1 power all the way down to plus 0. So what we're doing is we are taking our power, multiplying it to the front, and subtracting by 1. Take your power, bring it down to the front, decrease it by 1. And the reason that this constant is 0 when you take the derivative is you're thinking about this as k times x to the 0 power, right? Anything to the 0 power is 1. So if you take that 0 and bring it down front, you're going to have 0 times k, which is going to give you a constant of 0. So what this would look like in a problem is something like this. If we had f of x equals 7x squared plus 3x minus 4, and we wanted to say what's the derivative, all we'd have to do is take the 2, bring it down front, and say 2 times 7x, 2 minus 1 is the first power, so 2 times 7x to the first, plus really we have a 1 right here, so we drop our 1 out front and say 1 times 3x, 1 minus 1 is 0, minus this is really x to the 0 power, so drop the 0 out front, 0 times 4x to the negative 1, and then we simplify. 2 times 7 is 14, x to the first, 1 times 3 is 3, x to the 0 is 1, so that's just going to be 3, minus 0 times 4 is 0, so we can say 4x, or 14x plus 3. And if you think about the graphs of these derivatives, I kind of told you that your power is going to decrease by 1 each time. So if you think about the graph of your original function, it's not going to look exactly like that, but we know it's going to be a parabola. We have one place where our derivative is 0. So we know the derivative 0 right here. We have a negative slope to a positive slope. So our derivative would look like a line. Our derivative has a linear equation. So that's where we have to drop down by 1 each time. Now there's a couple of things we have to be careful of when we're using our power rule. The first is it only works when we have a variable to a power. It doesn't work with something like this. If we have f of x equals the square root of x plus 3x to the 4th plus x squared. The reason it's not going to work here is we don't have a power for that first term. So we can't take the derivative as it's written. But we can, since we are smart, rewrite this square root of x as something like x to the 1/2 power plus 3x to the 4th plus x squared. And that's going to allow us to use our power rule. So f prime of x would be 1/2 x subtract by 1, so negative 1/2 power, plus drop the 4 down. 3 times 4 is 12, x to the 3rd. Drop your 2 down, 2x to the 1st. So that would be your derivative. Now, things that you need to remember. Third root of x is going to be x to the 1/3. The third root of x squared is x to the 2/3. So what we need to remember about our powers, our exponents from radicals, is whatever root you're taking is the denominator of your fractional exponent. So if you think square root, this is the second root, so the 2 became your denominator of your fractional exponent. The other things we have to be careful of are products and quotients. So if we have something like f of x is equal to x plus 1 times x plus 3, we can't take that derivative because we're multiplying stuff. The only thing that we can take the derivative of is something that looks like a polynomial. The exception being if we have something like this technically isn't a polynomial because we have a fractional exponent, but it looks like a polynomial. What we have in this problem doesn't even look like a polynomial, and we don't have a rule for multiplication yet, so what we'd have to do is actually multiply this problem out. So we'd get x squared plus 4x plus 3, and now it's a polynomial, and we can take the derivative. So f prime of x would be 2x plus 4. So drop your 2 down front, drop your 1 down front, multiply, decrease your powers by 1, and we get 2x plus 4. If a problem asked you to find, say, f prime of 3, what you would want to do first is find f prime of x then plug in your 3. So f prime of 3 for this problem would be 2 times 3 plus 4 would be 10. So if you were to graph this function and look at it at the point 3, the slope is going to be 10. The last thing we need to look out for, we don't have a rule for products. We also don't have a rule for quotients. Not all quotients we're going to be able to get rid of. Let's say 3x to the 4th plus 2x squared plus 7 over, what does it say, x. Now, we're not going to be able to get rid of every quotient and turn it into a power rule problem, but some of them we will, and those special ones look like this. We have a special name for them, and we're going to call problems like this STDs. We don't want STDs. What STD stands for is a single term denominator. So if you look at your problem, you just have a single term in your denominator. You don't have x plus 1, you don't have x squared plus 7, it's just x. So since it's just x, if it was x squared, if it was 3x squared, it would work the same because there's no plus or minus. We still have the one term. We can simplify our fraction before we take a derivative because we don't have a rule for quotients yet. So we would want to divide each term individually. So 3x to the fourth divided by x is going to be 3x to the third. 2x squared over 2x is going to be 2x. 7 over x is going to be 7 over x. And that's not really helping a whole lot because we still have a quotient here. But what we're allowed to do with this is play around with our exponents again. We can turn this into 7x to the negative first power. So whenever you have a fraction in your denominator, don't forget that just means, a variable in your denominator. Don't forget that that just means it's a negative exponent. So there's your function that we can take the power rule on very quickly and very easily. So all we would have to do is take the 3, drop it down front. So 3 times 3x. 3 minus 1 is going to give us 2. Plus we have a 1 here for our power. Drop it down front. 1 minus 1 is 0. Take your negative 1, drop it down front. Negative 1 times 7. X, and this is where a lot of people are going to make the mistake. Don't forget we are subtracting 1. So negative 1 minus 1 is actually negative 2. And then we simplify. So 3 times 3 is 9x squared. 1 times 2 is just 2. X to the 0 is 1, so we don't have to write x to the 0. Negative 7 x to the negative second power. So that is your your power rule for derivatives.